This video is for section 18.3 about reversible chemical reactions and equilibrium. The first learning goal is to understand what happens at the molecular level in a chemical system at equilibrium. The second learning goal is to know three stresses that can change the equilibrium position of a chemical system. Let's look at that first learning goal. Understand what happens at the particle level in a chemical system when it is at equilibrium. Almost every chemical equation that we've seen this year, the arrow has pointed to the right only. But in reality, many reactions can occur in the reverse direction. A double arrow is used to show this. A reversible chemical reaction is a reaction in which the conversion of reactants to products and the conversion of products to reactants occur at the same time. Another word that could go on that blank is the word simultaneously. Here's an example reversible reaction. SO2 combines with O2 to produce SO3. But notice the double arrow symbol indicating that this reaction also occurs in reverse. The SO3 is decomposing to create SO2 and O2. Let's say that this reaction is happening in a closed container. At the beginning, there's a lot of SO2 and O2, but no SO3. So the forward reaction occurs at a quick rate. But as the SO2 and O2 are used, the forward reaction will slow down. In a previous lesson, we learned that one of the factors that affects the rate of a reaction is the concentration of the reactants. So as reactants are used up and there is less of them, the rate of the reaction will slow down. At the same time, the amount of SO3 is increasing as it's being produced, and so the reverse reaction will start to happen. There will be some point in time that the rate of the forward reaction is equal to the rate of the reverse reaction. That point in time where the forward rate and the reverse rate are equal to each other is called the equilibrium point. Chemical equilibrium is a state of balance between the rate of a forward reaction and the rate of a reverse reaction. When a reaction is in equilibrium, both the forward and reverse reactions continue. But because their rates are equal, there is no net change in the amounts of the reactants and products. Chemical equilibrium is a dynamic, not a static state. What this means is that the equilibrium point can change, depending upon the conditions that the reaction is under. The equilibrium position of a reaction refers to the concentration of the reactants and the concentration of the products at the point that the reaction is in equilibrium. So at the time that the forward reaction rate is the same as the reverse reaction rate, the concentration of the reactants and the products could be measured, and the relationship between those concentrations is referred to as the equilibrium position for the chemical reaction under a certain set of conditions. Here's an example. A reaction converts substance A into substance B. Let's say that the system is in equilibrium when the mixture is 10% substance A and 90% substance B. Write a chemical equation showing this equilibrium position. When you write an equation, reactants go on the left side, products go on the right side. A, we draw an arrow, and then put the B. This is a reversible reaction, so we make a double arrow. Underneath the A and the B, we can indicate the relative concentrations of the two substances when the system is in equilibrium. 10% of the substances in the overall mixture is substance A, and 90% of the mixture is substance B. sometimes you'll see this shown using arrows that are not the same length. For instance, A with a right arrow pointing to B, and then the left arrow is shorter. This notation indicates that this particular chemical reaction favors the creation of the product, substance B, resulting in much greater concentration of substance B in the overall mixture that we're calling our system. Now example 2, a reaction converts C to D. It's in equilibrium when the mixture contains 85% C and 15% D. Write an equation for this. So C with a double arrow and D. Underneath the substances, put the percents. This notation says there's a chemical reaction that is reversible. Substance C is changing into substance D, while at the same time, substance D is changing into substance C. At equilibrium, however, there is more of substance C than substance D. An alternative way to show this is to use arrows that are not the same length. This notation shows that the formation of substance C is favored. When the reaction is in equilibrium, meaning that the rate of the forward reaction is equal to the rate of the reverse reaction, there is more of substance C in the mixture than there is substance D. Now the second learning goal. Know 3 stresses that can cause a change to the equilibrium position of a chemical system. 3 things that affect the equilibrium position are changing the concentration of the reactants or the products, changing the temperature, and changing the pressure. If a chemical system is in equilibrium, meaning the rate of the forward reaction is equal to the rate of the reverse reaction, but then one of these changes occurs to the system, then the equilibrium position is going to change, meaning that the relative concentrations of the reactants and products are going to change. There is a scientific principle that applies to this. It is Le Chatelier's principle. If a stress is applied to a system that is in equilibrium, the system will change in a way that relieves the stress. Let's consider this example. Here is a reversible reaction. H2CO3 is decomposing into these 2 substances. But at the same time, the 2 substances on the right side are combining to create H2CO3. Let's assume that equilibrium has been achieved. The rate of the forward reaction is equal to the rate of the reverse reaction. And at that point in time, called equilibrium, there will be a certain concentration of the different substances in the system. Now let's have something change. What will happen to the equilibrium position if CO2 is added to the system? If there's more of this substance suddenly introduced into the container holding this mixture. Le Chatelier's principle says that the system will respond in a way that relieves that stress, in a way that overcomes that addition of CO2. So how does the system respond when more CO2 is added? It's going to respond by using up the CO2. CO2 is used when it combines with the water to create the H2CO3. The equilibrium position is going to shift to the left. When CO2 is used up by combining with water, more H2CO3 is created. The concentration of H2CO3 is increased while the things on the right are being decreased. Another way that this same question is frequently answered is to say that the reaction will favor the creation of the reactants. This phrase is saying the same thing as the equilibrium position shifts to the left. If more CO2 is added, then that extra CO2 has to be used up. The way the CO2 is used up is that it combines with the water and creates the H2CO3, which is the substance on the reactant side of this original chemical equation. Now, number 2, explain what happens to the equilibrium position if CO2 is removed from the system. Le Chatelier's principle says the system will respond in a way that overcomes that stress. So if CO2 is removed and you want to overcome that, then more CO2 needs to be produced. CO2 is produced when the forward reaction occurs. So the equilibrium position will shift to the right. Alternatively, you can say that the chemical reaction will favor the formation of the products. Number 3, explain what happens to the equilibrium position if H2CO3 is added to the system. So if more of this is added, the system will respond by using up the extra H2CO3. It's used up when the forward reaction occurs, creating the CO2 and H2O. So the equilibrium position will shift to the right. Although the chemical equation is reversible, both forward and reverse reactions are occurring at the same time, the forward reaction will be favored. Here's another example. N2 plus 3H2 makes 2NH3 plus heat. And notice the double arrow indicating this is a reversible reaction. What happens to the equilibrium position if heat is added to the system? So if more heat is added, the system will respond by using the heat. Heat is used when it combines with the NH3 to create the substances on the left side of that equation. So the equilibrium position shifts to the left. Another way to say that is the reactants are favored. Explain what happens to the equilibrium position if heat is removed from the system. If there's less heat, the system will respond by replacing that lost heat. Heat is created when the forward reaction occurs. So the equilibrium position will shift to the right. If a chemical reaction involves reactants and products that are gases, then changes in pressure can affect the equilibrium position. Here's an example. Nitrogen gas plus hydrogen gas makes ammonia. And this reaction is reversible. Question 6. If the volume of the container enclosing the reaction is decreased, then pressure will increase. Explain what happens to the equilibrium position when pressure increases. Le Chatelier's principle says, to overcome this stress, the system will respond by decreasing the pressure. So let's think about how pressure could be decreased in the container. To have less pressure in the container, there needs to be fewer particles in the container, striking the sides of the container. So let's look at this chemical equation and think about it in terms of particles. On the left side, there is 1 molecule of N2 and 3 molecules of H2. Or alternatively, you can think of this as there's 1 mole of N2 for every 3 moles of H2. Adding these together, there are 4 molecules or 4 moles of the substances on the left side of the equation. On the right side, there is a 2 in front of the NH3. There are 2 molecules represented here. The left side has more particles than the right side. To decrease the pressure, we want to change 4 molecules into 2 molecules. And that occurs when the reaction happens in the forward direction. So the equilibrium position shifts to the right. The reaction, while it is reversible, will favor the creation of the product NH3. Next, number 7. If the volume of the container enclosing the reaction is increased, then pressure will decrease. Explain what happens to the equilibrium position when the pressure decreases. Le Chatelier's principle says that the system will compensate for this by doing something that will increase the pressure. To increase pressure inside a container, we need to have more gas particles. The left side of the chemical reaction has 4 molecules, and the right side has only 2 molecules. To increase the number of particles in the container, the reverse reaction needs to be favored. The equilibrium position shifts to the left. Observe that in the case of pressure changes, the way that the stressor is relieved is by increasing or decreasing the amount of particles. Use the coefficients to see the relative number of particles on each side of the arrow. This concludes the video about lesson 18.3.